geobyte.
Let us take the another important problem. It is asking like this. A refrigerator works between 4 degrees centigrade and 30 degrees centigrade. It is required to remove 600 kilojoules of heat energy per second in order to keep the temperature of the refrigerator space constant. That means a refrigeration effect, amount of heat removed from the refrigerated space means cooling effect. Refrigeration effect is given 600 calories per second, right? But given 1 calorie equal to 4.2 joules, it is equal to 600 into 4.2 joules per second. And refrigerated space temperature T1 equal to 4 degrees centigrade, it is equal to 4 plus 273. And T2 equal to higher temperature where the heat is rejected, 30 degrees centigrade, this 30 plus, let me write it clearly, it is 30 plus 273. 30 plus 273. It is 277 Kelvin. This is the 303 Kelvin. Okay. Then you are asked to decide what is the power required. Okay, power required. As you know, the COP of the refrigerator equal to, right, lowest temperature T1, which is in Kelvin, T1 plus, right, T1 which is in Kelvin by uh, T2 minus T1, it is equal to refrigeration effect divided by the power. Refrigeration effect power. Let us take another slide. So COP of refrigerator equal to T1 which is in Kelvin by T2 minus T1. Since it is the difference, we can take either Kelvin or degree centigrade. T1 which is in Kelvin equal to refrigeration effect by power. From this, power equal to refrigeration effect into T2 minus T1 divided by T1 in Kelvin. T1 in Kelvin. Refrigeration effect is 600 into 4.2, 4.2 into T2 minus T1. Since the T2 minus T1 is the difference, I can write either in degree centigrade or Kelvin. I can write directly 30 minus 4. 30 minus 4 divided by the denominator should be in Kelvin, 277. Right? Simplified. 600 into 4.4 into 4.2 1 minute. Is it 4.2 or 4.187? Let's see. 4.2 only. 4.2 only. 4.2 into 20, 30 minus 6, 26 divided by 277. You simplify this value for getting 236.5 joule per second or watt. That is the answer. Okay. So look at the option C. Option C is absolutely correct. Understood clearly? Are you following clearly? Yes. Similarly, look at this problem. It is asking like this. A gas is compressed isothermally to half its initial volume. That means final volume V2 equal to 2 times half of the initial volume. Final volume is becoming half of the initial volume, V1 by 2. Okay. The same gas is compressed separately through an adiabatic process until its volume is again reduced to half. Then different options are given. Compressing the gas isothermally will require more work to be done. B. Compressing the gas through the adiabatic process will require more work to be done. Option C. Compressing the gas isothermally or adiabatically will require the same amount of work. Option D. Whichever the case, whether the compression through isothermal or through adiabatic process requires more work will depend on automatically of the gas, right? Atomicity of the gas, right? It is not like that. If I take the PV diagram, pressure versus volume diagram, Let us take the initial state. This may be the initial state where the volume occupied by the gas is V1. The final volume V2 equal to half of the V1, V1 by 2. If I compress the gas, isothermally, the isothermal compression process may be like this. For the same final volume, because the volume after compression in both cases remaining same. If it is compressing by adiabatically, the compression should be marked like this. 1 to 2 dash. Let me write it. 1 to 2 isothermal compression. Isothermal compression, and 1 to 2 dash, 1 to 2 dash adiabatic compression. Adiabatic compression, because the slope of the adiabatic curve is more than slope of the isothermal curve. The slope of the adiabatic curve is minus gamma p by v. Slope of the isothermal curve is minus p by v. For both cases, negative sign indicates as the pressure increases, volume decreases during the compression process. Right? In both cases, negative sign with the slope indicates as the pressure increases, volume decreases during the compression process. Okay. Now, as you know, area below PV diagram, PV diagram for a process represents work, thermodynamic work. Okay. Then work required for isothermal compression equal to area below 1 to 2. Area below 1 to 2. Whereas work required for adiabatic compression, work required for adiabatic compression equal to area below 1 2 dash. Look at the diagram. Area below 1 2 dash is more than area below 1 to 2. That means area 1 2 dash KL1 is the adiabatic work, whereas area 1 to KL1 is the isothermal work. So from this I can say that work required for adiabatic compression is more compared to work required for isothermal compression. That is the answer. Okay. Now look at the options. Look at the option B. Compressing the gas through the adiabatic process will require more work to be done. Absolutely correct. Option B is absolutely correct. Understood clearly? Yes.
Geobyte.